So, as you said, I'm John. I work at NIST Boulder, and I'm an experimentalist, primarily interested in superconducting circuits and microwave optomechanics. My background is in the low-temperature microwaves, working in Josephson junction groups, and did a postdoc with Conrad Leonard, where I learned everything I know about nano and micromechanics. And now, today, what we're really doing is combining all the good things from both worlds to see what we can do, ideally, to address quantum vibrations. What can you know quantumly about a mechanical mode, and its measurement, its preparation, what you can do with it. So, in this overly sexy-looking cartoon, what you see here is a type of circuits I'll be talking about today. They're sort of simple inductor capacitor circuits. It forms an electromagnetic mode that resonates at gigahertz frequencies. And then this capacitor has a top plate that's mechanically compliant. It can vibrate with frequencies that are megahertz or tens of megahertz. So we'll use our exquisite control and measurement of this gigahertz electromagnetic mode to address this mechanical mode. And the beauty of these circuits is we already know how to do this at pretty low temperatures. You can stick it in a low temperature cryostat and start out with a big head start in how cold this drum can be. So all the work I'll talk about is work done at NIST in collaboration with Ray Simmons' group, and some of the work is also in collaboration with my former postdoc group, that of Conrad later. I'll point out as I go. So over the 3 lectures, this first lecture I'm going to spend a lot of time trying to articulate how you think about microwave photons as photons, or how you think about these circuits as an optomechanical system, how you can compare and contrast them to the standard Fabry-Probe cavity with a mechanically compliant mirror. I'll give a little bit of history. This is actually a quite old field and quite rich, and take you through some of the progress that led to these sorts of circuits that we're working with today. Yes, just as I said, I will do these things. In the next lecture, I'm going to move on to sort of the experimental results that we've had. Things like performing sideband cooling and using pump and probe techniques to measure some of this optomechanically induced transparency, this EIT physics that we've already heard a little bit about this week. And then with the last talk, I'll move more on to not state preparation of mechanics, not cooling, but actually quantum measurement. Much more like Ash had talked about in his lectures. Can you reach the standard quantum limit, the so-called quantum limit, all the quantum limits people can talk about? I'll open up with telling you something I'm sure you already know. The Nobel Prize this year went to Dave Wineland and Serge Haroche, and it really warms my heart at a deep level, not just because Dave Wineland literally works across the hall from us at NIST, but because it combines 2 of the things I love. The citation is really for doing quantum-y stuff in general. Specifically, what I like in the Wineland group, with the triact ions, they're really controlling the quantum motion of a mechanical degree of freedom. And in their case, the mechanical degree of freedom is a single ion, but it's really the pioneering work that talked about encoding quantum information and really doing quantum measurement to exploit that. On the other hand, Serge Haroche really is like the prime example of beautiful quantum optics. And what I also love here is that the optics is microwave. These photons are gigahertz photons, and he works at low temperatures so that the electromagnetic field is really quantized. And you can do some of the best examples with quantum optics with microwave photons. And I'll explain what it means to be in a regime where you really can and must consider the microwaves to be photons. In both these systems, they use an atomic system as the intermediary to go between them. What I'd like to do is just cut out that middleman, get rid of the atoms in the circuit, and use the quantum microwave photons to study the mechanical motion. So broadly speaking, if I have a bosonic mode, it could be electrical, it could be mechanical. You're going to be talking about BoseEinstein Statistics. We all know the harmonic oscillator is quantized, as we've already heard people go over briefly. And you could ask for any harmonic oscillator at any given temperature, what's the chance I'd find it in its ground state? Because there's always some chance. If I probe the system, I can find it in its ground state. We know this is just governed by BoseEinstein Statistics. And the probability that I would find it in the ground state is proportional to sort of 1 over this occupancy. So that if I were very, very cold, well, this goes all the way to 0, and I would be in the ground state with near unity probability. So you don't think about this much with traditional quantum optics, and there's a good reason for that. If I start off with, say, a micron wavelength light, 300 terahertz frequencies, 300 Kelvin room temperature noise, what is this n factor? My laser pointer's dying. Oh, there it is. This n factor. Well, h bar omega is something like 50 kT. So you have an e to the 50 in the denominator here. This gets very, very small and completely negligible. Unfortunately, that's not the case for microwaves, and certainly not the case for any of the mechanics we'll consider. So if I take 3 kind of canonical modes, a Fabry-Perot cavity at 300 terahertz, as I said, this n is very, very small, and this probability is, for all intents and purposes, 1. For microwave modes, kind of 10 gigahertz is sort of the canonical frequencies we're thinking about. At room temperature, you'd be talking about a few hundred or 1,000 quanta. So any of the quantum optics you would try to do, you could do, but they're not true coherent states. They would be displaced thermal states, and you would be stuck with the thermal statistics. If you cool to sort of 50 millikelvin, a completely reasonable temperature you can do with commercial dilution refrigeration, well, now h bar omega can be kind of a factor of 10 larger. This n can be a small number, and you're now talking about how many 9s of probability are in the ground state. And this is really the beautiful regime that all the stuff we've heard Steve Gervin talk about, the superconducting qubits are exploiting. Now with the mechanical modes, for the work we'll talk about today, talking about 10 megahertz, at this same 50 millikelvin, well, it helps a lot. You've now cooled the mechanical mode to something like 100 quanta, but that's still very, very classical. There's still only a 1% probability, or 1% of the time is this mechanical oscillator spending time in its ground state. And we're going to use this as our starting point to then do sideband cooling techniques to get this much, much colder, to see if we can get this probability to be ground state much closer to 1, to really realize a low entropy system in a mechanical. So I'm going to reiterate many of the things we've heard this week. I'm going to say it in my own language. I'm going to hopefully go quickly and just taint it with my own personal opinions as I go along the way. The simplest way I can think about optomechanics and what happens there is if I want to know where something is, I can scatter something off of it. A logical thing to scatter off it might be shine a laser and just look at what comes back. If this boundary condition moves, I will shift the phase of the laser that comes back. And if this boundary condition is moving harmonically, well, now I will encode these vibrational wiggles as phase modulation of the light. So I put in light at one frequency, and I look at what light comes out, and I can see something special happens. I now get light out at different frequencies than I put it in. This is the heart of the fundamental nonlinearity of radiation pressure or these sort of optomechanical interactions. Nonlinear in the sense that I put in light at one frequency and it came out at different frequencies. There's a fundamental mixing product that goes on here, and that is purely through this interaction. Now you can of course do better than just bouncing off one boundary condition. You can create a standing wave, you can have a resonance here. That resonance sharpens up your transfer function for you. It gives you a much steeper sensitivity, so a unit change in motion now gives you a much bigger phase shift. Your sidebands are much, much bigger. And that's why coupling to an electromagnetic resonance really enhances your measurement sensitivity. But it also necessarily is enhancing the radiation pressure forces, how much you're interacting with this mechanical mode, or you're able to boss it around just with these radiation pressure forces. Now, as I've drawn it here in the cartoon, I've done it all with optical light, but what you should always keep in mind is this is a completely generic argument. There's nothing special about Maxwell's equation that says this is any different at microwave frequencies. I could easily have a microwave Fabry-Perot cavity, or actually what's more interesting is the ability to make these lump circuits. And I'll tell you why that's special. But again, you just interrogate it with a microwave near this resonant frequency and look at what comes back out. And now if you're looking at this, I mean, depending on who you ask, you can think about Raman spectroscopy and Stokes and anti-Stokes sidebands. You can think about three-wave mixing. Looking at it this way, it looks more like an FM radio. These are all really, really the same thing. And they're all the same physics, and that's what that's gonna be the theme throughout the talk today. So as I've drawn it in the cartoon, you're driving the circuit exactly on resonance. There's nothing to break the symmetry between what's going to take light that comes in at your drive frequency and converts it into a higher energy photon or a lower energy photon. But this cavity now does something else special for you. And that gives you an electromagnetic density of states. And this is, again, the cartoon version of sideband cooling. If I drive off resonance, there can be an enormous density of states for one of these processes, a low density state for the other process. And again, depending on your background, you might think of this as some sort of Purcell filter. You might think of this just in an AMO community as the traditional sideband cooling requirements. And as you can see from this cartoon, what you really want to do if you want to get significant cooling is you need the line width of this cavity to be narrow with respect to the spacing of these two lines. That's the so-called good cavity limit that we've heard over and over about. So just to be very clear, I mean, to point out what we're doing with these mechanical circuits is very much exactly in the style of the trapped ions and what the trapped ion community was doing 30-some years ago now. And we're just trying to build this up to see if we can do it with engineered circuits, not with a single atom, but with large things that we can hope to engineer exactly to do whatever we want with. So, as a little aside, it's unfortunate that Steve isn't in the room here, but what Steve told us over and over is that Josephson junction is the only, and always underlined only, no nonlinear, non-dissipative circuit element. And it's not just Steve. I can picture Michel Devray and Bob Schulkopf standing behind them, also making these statements. And what he means by that is most nonlinear circuits you can think about, things like diodes, they get their nonlinearity in a way that's inherently dissipative. The Josephson junction, as we've heard, acts like a nonlinear inductor whose inductance depends on how much energy is in the system. What I'm going to pose for you today is to think about another circuit element, maybe one that's not so surprising. Let's think about a capacitor that's mechanically compliant. So now you have an LC resonance here, and as I would put more and more energy in this circuit, well, something's going to happen. There's now electric fields between the plates of the capacitor that will pull it closer, and that means my capacitance changes. In much the same way as my inductor becomes a higher inductance with more power, my capacitor gets bigger capacitance with more power. And both of these show that same style of nonlinearity. Just to go through the steps in a little more detail, you can imagine, let's say I excite this with some microwave voltage. There's a force that's proportional to this voltage squared. And if there's an ability for this, the plates of the capacitor to change, it will. That's what's quantified by this dCdx. Well, that's going to pull, and it depends on the spring constant, how much it will pull. And then you'll get some change in the capacitance, because we're considering here just a parallel plate capacitor. And the total capacitance depends on the separation. So if you take all these and combine them together, what you get is exactly the same nonlinearity. And I won't bore you going through it, but if you change all the units to the units we're interested in, what you get is now a resonant frequency for the circuit that depends on the number of photons you put in the circuit. The number of photons here is really just proportional to this voltage squared. It's just a measure of the energy in this oscillator. And so you get this term that is over here. It depends on the coupling between the mechanical mode and the electromagnetic mode, the G0 that we've heard about, and I'll go into more detail later. And this is a quantity that, in general, is very, very small. So while this nonlinearity is there, I'm not going to fault Steve for making his claims. I mean, really, the nonlinearity of the Josephson circuits is many, many orders of magnitude larger. It can be nonlinear at the single photon level or much, much less. In fact, that's what you mean by a qubit, something nonlinear at less than a single photon. Whereas for the optomechanical circuits, you're nowhere near there. So I will support his statement in practice, but I will point this out in theory. There could be other ways to get nonlinear circuits. And this is part of the research that I'd like to explore. How do you really push these parameters to see these types of effects? So all these systems, whether you're talking about LIGO or microwave, have the same interaction Hamiltonian.
We've seen it a lot, so I'll go quickly. I've now wrote it in this very quantized looking natures with A's and A daggers and B's and B daggers. I wholeheartedly agree with what Keith Schwab warned us about the other day. Just because you can write down raising and lowering operators doesn't necessarily mean you're doing anything fancy or quantum. Oftentimes, it's nice because it gives you nice dimensionless units, and it's an easy way to think about. But throughout, when you see an experimental result, you should ask yourself, is this quantum, is it classical? What if each bar had a different value? Would that change the outcome of what you're doing? So in the fully quantum language, the displacement operator looks like this. It's a B dagger plus B. The prefactor is just the 0-point motion of the mechanical oscillator, how much it would be vibrating if it had no energy whatsoever. What's important is that if you want to make this large, you need to do two things. You want a low mechanical resonant frequency, and you want a low mass. In other words, you want the floppiest possible thing that moves a lot, even from its quantum motion. And if it moves a lot from its quantum motion, it will also move a lot from its thermal motion or whatever motion you have. So trying to optimize this and make it large is what's pushed much computing to go to nanomechanical structures, just for the low mass. Unfortunately, that tends to push your frequency up and tend to also shoot yourself in the foot. So many of these things are a compromise. Now, if you want to realize, optimize everything here, you don't want to just optimize this displacement here, but you need to optimize the other side of the Hamiltonian. So if this is a displacement, what's here on the left must be a force, and that really is the force per photon you get. This is just radiation pressure physics. The capital G here I've written, how I have written it, is this factor of how much the cavity frequency shifts per unit motion, which you can calculate for any one of these systems. And again, you have another trade-off, because you can't just optimize the frequency shift per unit motion or the unit motion. You really care about the product. And this product is precisely the G0 I referred to earlier. This is the single photon coupling rate. This is how much these two systems are coupled. Even though they're at very different frequencies and completely different in nature, there still is literally a rate. This frequency tells you how often the rate at which these things are exchanging energy. And you can naturally ask whether this rate is large or small compared to the dissipation problem. So this is the quantity you want to optimize. How do we think about it? Just to flash up the zoo of different structures, you're probably aware, sort of the canonical system of a fabric row cavity with a mechanically compliant mirror is fading out of the picture as more and more of these structures are going to more exotic things. And they're going to more exotic things precisely because they're trying to optimize these parameters. So these sorts of structures really are, you can see a micro-machined mirror, some Bragg mirror forming one end of a cavity. You can also use nitride membranes, tried here by the Harris group. Or you can use some of these more the tools of micro and nanolithography to bring resonators, like the toroids, or microspheres, or even the optomechanical crystals here. And just in looking at these, if you try to think about the couplings, the ones in which you can really see the size of the electromagnetic cavity and the size of the mechanical degree of freedom in the same picture are to give you a hint that maybe you're doing a good job of interacting the two. And that's why with these sorts of structures, these will have the largest G0s out there. The bare coupling strength are really favoring the smaller objects. But that's not the whole story. You really care about things like dissipation, and that's where a lot of these ones truly shine. And that's the good old-fashioned optical optomechanics, but there's also microwave optomechanics, and there's a long history here, dating back to the work of Perginsky. There's a long history at University of Western Australia in the context of LIGO, really using resonant cavities. And then in the late 2000s, people really pushed using the tools of nanolithography to realize these same optomechanical circuits. That's work I worked on at Gilla, also simultaneously in Keith Schwab's lab. More recently in Finland, there's also very similar circuits. So for the canonical touchstone system, a fabric row cavity with a mechanically compliant mirror, how do I think about this G0? Well, it's insanely simple. The cavity frequency shift per unit motion is just the cavity's resonant frequency divided by the length of the cavity. And then to turn that into a G0, I need to multiply by the motion of the mechanical mode in its 0-point energy. And so what you see is this very important ratio of the 0-point motion to the length of the cavity. And this is why you could use a very, very high Q, very high finesse fabric Perot cavity that's many, many wavelengths, but you'll start to throw away this coupling strength. And as you push your mirrors closer and closer together to really up this interaction strength, to really increase the force per photon, you might then suffer from increased dissipation. Now you might say, how much can I push this? Well, in this standard picture, I have to be able to fit at least a half wavelength between these mirrors. So this picture kind of breaks down if my mirrors were to get less than a half wavelength apart. And some of the things with the optomechanical crystals are starting to bend this condition. They're getting really confining the light to something less than a wavelength in the index contraction. What's very, very nice about the microwave domain is I don't have to use fabric Perot cavities. I can really use a lumped circuit. And the definition of a lumped circuit are using elements that are much less than a wavelength, where there's nothing here that's lambda/4 long. And that's a good news, because microwave lambdas are very, very long. You're talking about centimeter wavelengths. But if you take this simple circuit with an inductor and capacitor and do the same analysis and say, how does this resonant frequency change? You get a very simple looking expression again. The characteristic frequency scale is now the frequency of the cavity, which gives us a hit of a factor of about 10 to the 4, because we're using a 10 to the 4 lower cavity frequency. Where you can win this back is you can hope to use smaller structures with larger zero-point motion, and then crucially, the characteristic length scale here is set by the separation between the two plates. And that's something that can be, and is in our circuits, much, much less than a wavelength. And so the lumped circuit really allows you to separate the electromagnetic field, the electric fields from the magnetic fields, and concentrate the electric fields exactly where you want them most, interacting with the mechanical system of interest. Now, this circuit diagram is pulled from Brzezinski's book from the late 80s. It's a circuit he's been thinking about for many, many years. And this expression I've written here is only an approximation. It's only true if the mechanically compliant capacitor is the only capacitor in the problem. If there's other parasitic capacitance, which you inevitably would get, that's going to dilute your coupling strength you get here. There's a sort of participation ratio. That's the ratio of the capacitance that moves to the total capacitance of the circuit. So being able to optimize and really focus all your capacitance here is what you would do to optimize this genome. So even a little more history, I recently found that before Brzezinski, circuits like this were being considered at Bell Labs. I found this beautiful paper, which I love, because the title of the paper is called Atomic Physics and Circuit Theory. And what they had in mind is they were really thinking about electrical circuits where they put a tuning fork in there, and this tuning fork vibrates around and changes capacitances. And they were really appreciating the fact that you have this nonlinear system. You have this system where you get frequencies coming out of the problem that aren't harmonics of the electromagnetic mode or of the mechanical mode, but are really the mixing products between the two. In fact, there's this nice, very powerful and prophetic statement in there that this phenomenon is very analogous to the Raman effect that was recently seen in AMO Physics. For those of you that might know, the Bell Labs is work by people like Hartley, who was a predecessor of other people like Manley and Rowe, who are really seminal in the formation of kind of nonlinear optics and thinking about it, again, originally from these electrical circuits. I don't have a slide on it. There's also in the 40s and 50s accelerator physics, where people were trying to build big microwave accelerator cavities just to get the largest electric fields they could and the largest magnetic fields they could. And in the literature, you'll see them talk about parametric instabilities. They were running into optomechanics whether they wanted to or not, because they were putting so much power in their systems. And so they spent a lot of time trying to figure out how to damp and get rid of these damn mechanical modes. I wish I could go back and see exactly what they were seeing at those times. The other thing I like about this, I found this in the NIST library. It's from 1929, and it's in the Bell laboratory record. And just to give you a scale of what Bell Labs was also working on at the time, the next article after this one was talking about a ringing machine for small offices. They're really talking about developing a nice ringer for your phone. So this is simultaneously at these sort of times. It gives you an appreciation for what was going on and how ahead of the time some of these things were. So As far as optomechanics, for the sake of optomechanics, very much Brzezinski is a founder in this field. And he had some very nice early experimental work that's shown in this cartoon here, and I'll describe it to you what the pieces are. So this long piece you see here is a piece of rectangular waveguide. It's just a transmission line for microwaves at about 7 gigahertz. It's about 1 meter long, and one end he left open, that's the boundary condition, and the other end he dangled a piece of aluminum foil. And he dangled it nicely off of good threads, so that this aluminum foil could vibrate like a pendulum mode at about 1 hertz, and that would modulate the electrical length of this waveguide. He then measured what this pendulum was doing as a function of the microwave power he put in there. So if we think about the systems, what do we have? Cavity frequencies of 7.5 gigahertz, very similar to what I'm doing. Cavity Qs of about 20,000, not bad for being at room temperature with waveguide. And this suspended foil, you're talking about hertz sort of frequencies, Qs of 100,000. I mean, ring down times that are close to an hour is what we're talking about here. And what he really showed, here in these measurements was that depending on if you apply the power in this cavity, red or blue detuned, you could see a difference in this ring down time of the mechanics. You could see the first realizations of damping. And the ring down times, again, are going from 70 minutes to 80 minutes. It's really a patient experiment. And if you think about what are the coupling strengths you have in this problem, well, you already have almost everything you need to know. The 0-point motion of this mode, given its mass, was about a femtometer, and the cavity frequency was only changing by about 1 hertz per nanometer. So this is giving you a G naught of sort of a microhertz. What you win back is by pumping this up with a lot of power. There are many, many photons here. I'm not even sure how many, but you're talking about watts of power. And sort of get this first realization of these mechanical damping. So I'll fast forward to experiments I was involved in and show you our version of these structures. So what we're fabricating is on a silicon chip, structures where we have a suspended aluminum wire. We're going to use aluminum, one, because it's a nice, light mechanical material, also because it superconducts at low temperatures, really helps us with the dissipation of the electrical system. And you'll see that this wire is part of this center conductor of a transmission line. And this transmission line is shown in red. It goes all the way out. It's meander that's a quarter wavelength long. So this realizes a quarter wave microwave resonator, where you have a short down here and an open circuit up here. So all your voltage is concentrated up here. That's precisely where we suspend this wire. A false color SEM zoom in here shows that this wire suspended maybe a few hundred nanometers from a ground plane. And as the wire would vibrate in the plane closer or further away from this counter electrode, it would modulate the capacitance of this element. That small change in capacitance will tweak the electrical length of this resonance, and that gives you your optomechanical coupling. So again, if you think about parameters, well, in terms of frequency and cavity Q, it's actually very similar to Brzezinski. Where things are very, very fundamentally different is now you're talking about mechanical frequencies of megahertz instead of hertz, and quality factors that are in that same ballpark, in the ballpark of 10 to the 5. The coupling you get here is now much, much bigger than Brzezinski, several orders of magnitude, and it's still something we'd like to make much, much larger. So what can we do to optimize this circuit even further? Well, as I told you before, if you want to optimize, you have a couple choices. You can make this separation closer, which, believe me, if we could, we would. You would always push that closer and closer. Unfortunately, you fight the practical effects that when you get two surfaces close enough, eventually they will snap together and not come back apart. So that's a lot about the art form of microfabrication. The other thing you can do is you can try to really minimize the capacitance in the circuit that doesn't have to do with this mechanical element. So to do that, we started going to resonant structures that now look more lump circuit-like. Instead of a quarter wave resonator, we have this kind of meander inductor. And another way to say that is we've increased the impedance of the cavity so that for the same resonant frequency, we have much, much less capacitance. And that ups this participation ratio and ups the coupling you get here. So now if you ask how much does the cavity resonant frequency shift for unit motion, you're talking about tens of kilohertz per nanometer. And with these devices already, we were able to do very interesting things. We could measure very, very strongly, measure close to the standard quantum limit of precision. And you could already see effects of sideband cooling. They just weren't quite strong enough to cool these mechanical loads to their ground state. So in the devices that we had, and the very similar ones that they were working on at Cornell and Caltech, you could do a lot of great things. And the great things you could do were thanks to the mechanical wires. They're really great. They're very low mass, very high Q. They have large zero-point motion. Large in this community is kind of tens of femtometers. But the coupling strengths were really limited, and they were limited precisely because of this participation ratio. So the structures that we want to go to are things that look much, much more like the cartoon. Really realize an inductor and a capacitor, and then allow the top plate of the capacitor to be mechanically compliant. And the ideas are, these are all the same nanolithography we were already doing. It's just a circuit that really takes advantage of what you have here. Now, what wasn't at all clear with these circuits is that these large drum modes could have the same mechanical cues, or that you would get the same dissipation in the electrical circuit. You're now concentrating all the electric field between these two plates. You might worry that you're concentrating it in a place that might have loss. So I'll go through a little bit of the steps of how we fabricate these things, again, to give you some of the experimental perspective. These vacuum structures are something they had started developing at NIST before I got there that I was very, very envious of. And the reason they were doing them in the first place was trying to make low-loss capacitors. What's been discovered over and over is that no matter what dielectric you put to make a good capacitor, that dielectric inevitably has some sort of loss tangent. And the loss tangent of that dielectric is what has been limiting the Qs of these planar microwave resonant circuits and the performance of superconducting qubits. So the general idea is get rid of the dielectrics, store all your electric field in the vacuum. Vacuum has a pretty good loss tangent because it's the vacuum, and that means that you should in principle win. So the idea of these structures that they were developing there is you put down, you start with a substrate of silicon or sapphire that's your dielectric. You put down your base layer of metal. It can be aluminum or niobium, whatever you would like. Some good, nice superconducting metal. You then put down a sacrificial layer, and that can be many things. For the cases of the things I'll describe here, it was silicon nitride. And then you put another top electrode on top of that. And you can make good metal contact to the first layer, and you now have this tri-layer sandwich. And what you can then go back in and do is you can plasma etch, and you can get rid of that dielectric. So you have these suspended structures. Now you can already, from these SEMs, start to see some of the problems with this. One, you can see that this nice ribbon here is actually popping up. And it's popping up because there's compressive stress that's built into this film. And really controlling these stresses in the fabrication is a lot of the heart of what we fight on a daily basis with the fabrication. Knowing what these structures would do, how they will buckle when you will release them, whether they'll be under tension or compressive stress, those sorts of things. The other problem you can have is if you take a large structure like this, here the top electrode of the capacitor is going all the way along here and forming this very narrow path. And if you want to try to undercut it, it's very hard to get in there and remove that material. So you can see we've created these holes for etching so that you can allow the etchants to get in and the material you're trying to get rid of to get out. So this is the fabrication techniques that I was salivating over before I came to NIST, with the ideas of now using these structures to make intentionally mechanically compliant. In fact, you can see here, they put in these capacitors post, specifically because they didn't want their structures to move or bend or to be vibrated. Because at the time they were just looking at low loss capacitors. So this is what one of our current circuits looks like. It's fabricated on kind of a standard chip, about 6 millimeters on the side. What you're looking at here is 3 separate transmission lines. We launch a signal, a microwave signal that goes down a coplanar waveguide transmission line and comes out the other side. Hanging off this transmission line are 6 different resonant circuits. You can give each one a different resonant frequency, and you can kind of naturally multiplex in a way that doesn't hurt you. If I want to talk to this circuit, I apply my signal near its resonant frequency at 7 gigahertz. If I want to talk to this one, I apply a signal at 5 gigahertz. These can be very well separated with respect to any of the line weights and anything we're talking about here. And so this is kind of a natural way to get more bang for your buck. Because we're going to have to measure these only at low temperature, cooling this down, it's very helpful to be able to measure more than one at a time. You take that chip and now you have to connect to it, and somehow the way you can do that is you can put in custom-made sample holders like this. The idea is you can get off the chip onto some commercial circuit board with wire bonds. You can literally connect the with wires between the center electrode to some outer electrode, and you can launch out onto a coaxial load. You can get onto some SMA connector, and then that allows you to address it in a completely plug-and-play way. So what's nice about these systems is they are pretty monolithic. With the mechanics, there's nothing adjustable at low temperatures, and even with the alignment, it's not like we're trying to align some feed line. It's all monolithic to the circuit. So this is a big advantage that we have, is that you can control all the electromagnetic signals because they go down a coaxial load. They interact very strongly in an engineered way with your circuit and come back. If you just had a microwave circuit sitting in free space and you shine some light on it, of course you can get power into the circuit, but the power that would come back out would be spread over the whole environment. So again, everything that I'm going to talk about in today's lecture and tomorrow's lecture is going to be a circuit of this style. We're going to probe the system completely with microwaves, spectroscopically. There's no DC voltages that are going in here. We're going to use microwaves to apply our forces and also demodulate the microwaves to infer what's going on with the system. Are there any questions at all as I've been rattling off? Feel free to just interrupt. So, zooming in a little more to the circuit,